Good morning, everyone. Today, our group is being assigned to report all about the Design-Via-Root-Locus, which is the feedback compensation. Presented below are the group members. Feedback compensation. In the previous groups, their report is all about the cascade compensation. It is a way to improve a transient response and a steady-state response immediately or independently. But in our group, we will discuss a new method to improve such responses in a different manner than the cascade compensation of function arranged in series, rather of feedback compensation or having a feedback function, which is being discussed in the previous chapter, in the chapter 5, which is entitled the reduction of subsystems. Cascading a compensator with the plant is not the only way to reshape the root locus into intersect the closed loop S-plane poles, which yields a desired transient response. Transfer functions is designed to be placed in a feedback path and can also reshape the root locus. So here are the difference of feedback compensation to cascade compensation. First is that compensator is at the feedback, as opposed to the cascade compensators. Here, the compensator is placed in a feedback position for the whole function. It can also be used in cases where noise is a concern if you use cascade compensators. It is also in the where noise problems prelude the use of the cascade compensation. More complicated than the cascade. So, since it may not require another amplification, and there are also lots of examples for this, but the given example in the book is that of the tachometer. Generally provide a faster response, so it may not require an additional gain. So here are the differences given of the feedback compensation than the cascade compensation. Below is a generic configuration showing a compensator HC of S, which is in place in the minor loop of a feedback control system. So here in the figure, it has been shown a sample of a function or a system in which it has a feedback function or a feedback control system. So here, the feedback control system is labeled as the HC of S. So if we let K and G2 be a unity value or equal to 1, the input to the feedback of the compensator, K sub F H sub C of S, is from a high-level output of G sub 1 of S, while the other output of K sub F H sub C of S is one of low-level inputs into the K sub 1. Thus, it happens to reduce the level through the K sub F H sub C of S, in which the amplification is often not required. So, the design procedures for the feedback compensation can be more complicated than for the cascade compensation. So, engineers have some kind of a luxury for the designing and the process or for faster responses into portions of a control loop in order to provide in isolation. Here is a popular feedback compensator is a rate sensor, or what I have said earlier, a tachometer, but here a rate sensors is applicable in ships and aircrafts. The rate sensor can be a rate gyro that responds with an output voltage proportional to the input angular velocity. In many other systems, so this rate sensor is implemented with a tachometer. So, tachometer is an instrument for indicating a speed of rotation. Usually, it is read in revolutions per minute or RPM. This compensator can easily be geared to the position output of a system. So, usually, it has been put in a rotating inputs or a rotating object to measure its rotational speed.
Below is an image of a position control system that uses a tachometer as a differentiator in the feedback path. Here we can see the potentiometer which is this part, is connected to the motor and the output potentiometer by a set of gears, which is through this wire, a set of gears and a set of gears. So we can also see that the output potentiometer is has a connection to the tachometer, which is this part, and you can also see that the tachometer has connection through this junction over here, and in this junction is connected to the gears, which forms a small loop within the system. So the block diagram representation of the tachometer is shown in figure A, and its typical position within a control loop is shown in figure B. So the typical position of the tachometer is in the minor loop of the system, which can we see in figure B. So typically, the design of feedback compensation consists of finding the gains such as K, K1, and Kf. After establishing a dynamic form for HCS, there are two approaches. The first is similar to cascade compensation. With the second approach, we design a specified performance for the minor loop, followed by the design of the major loop. So approach number 1. So assume a typical feedback system where GS is the forward path and HS is the feedback. Now consider that a root locus is plotted from GS to HS. With cascade compensation, we added poles and zeros to GS. With feedback compensation, poles and zeros are added via HS. So in figure A, we can see a generic feedback system, and in figure B, we can see the generic the system after applying feedback compensation using approach number 1. So the first approach consists of reducing figure A to figure B by pushing K to the right past the summing junction, pushing G2S to the left past the pickoff point, and then adding the two feedback paths. Figure B shows that the point loop gain GSHS is equals to K1 G1S multiplied by KFHCS plus KG2S, and this serves as our equation 9.36. So without feedback, KFHCS or the loop gain is GSHS is equals to K1 G1S multiplied times G2S. So thus the effect of adding feedback is to replace the poles and zeros of G2S with the poles and zeros of KFHCS plus KG2S. So hence this method is similar to the cascade compensation in that we add new poles and zeros via HS to reshape the root locus to go through the design point. So however, one must remember that zeros of the equivalent feedback shown in figure B, HS is equals to KFHCS plus KG2S over KG2S are not closed loop zeros. So for example, if G2S is equals to 1 and the minor loop feedback KFHCS is a rate sensor, KFHCS is equals to KFS, then from the equation 9.36, the loop gain is JSHS is equals to K1 G1S multiplied by S plus K over KF. So thus a zero at negative K over KF is added to the existing open loop poles and zeros. This zero reshapes the root locus to go through the desired design point. A final adjustment of the gain K1 yields the desired response. So again, you should verify that this zero is not a closed loop zero. And approach number 2. So the second approach allows us to use feedback compensation to design our minor loops transient response separately from the closed loop system response. In the case of an aircraft, the minor loop may control the position of the aero surfaces, while the entire closed loop system may control the entire aircraft's pitch angle. So, the second approach for the feedback compensation can be summarized by first designing the minor loop, then designing the major loop. So, the minor loop is designed to change the open loop poles and open loop transient response. Loop gain is used to adjust the closed loop performance.
Example 1 for approach 1. This is for the unity feedback system in figure 9.1. GS is equal to K over S multiplied by S plus 2 multiplied by S plus 4 multiplied by S plus 6. The question is design rate feedback to yield a step response with no more than 15% overshoot and no more than 3 seconds settling time. Use approach number 1. So the given is already two givens, the 15 overshoot and the 3 seconds for settling time. So here's the solution. In order to get the overshoot, the damping ratio, so PO is equal to E to the exponent of negative damping ratio multiplied by pi over square root under 1 minus damping ratio to the square root of 2. So when you put it in the calculator, you will get a 0.517. So the desired operating point is found from the desired specification. So the formula with the settling time is damping ratio multiplied by Wn is equal to 4 over Ts. 4 is the common factor. So equals 4 over 3, we get a 1.333. So the formula for Wn is equal to 1.33 over damping ratio, we got 2.578. Thus, Im is equal to Yn multiplied by square root 1 minus damping ratio squared. So as we got and replace the factors, so we got 2.207. Hence the design point is 1.33 plus J, and for the y-axis 2.207. The angular contribution of the system poles and compensator 0 at design point is 108. Thus the compensator 0 must contribute 180 minus 100.8 equal to 79.2. Using the geometry below, as you can see at the diagram, you got the negative ZC and negative 1.33 with an angular of 79.2 and at S plane at J. So as for the formula goes, we got 2.207 over ZC minus 1.333 equals tan of the angular angle. So hence the ZC when put at the calculator, it is 1.754. So the basic from the problem formula, there will be additional besides the K. So it will be K multiplied by S plus 1.754 from ZC. So as you can see, 1.33 plus 7 plus J 2.207 yields K equal to 47.28 with the highest order at 1.617 and negative 7.718. Following figures, as you can see in the formula, 1 over key f is equal to 1.754. So, the key f is equal to 0.57101. Also using the notation of the figure, so K1 is equal to K1 multiplied by Kf is equal to 47.28 coming from yield. So the K1 is equal to 82.93. That's all.
Here we have an example of approach number 2, which again in approach 2, it will allow us to use feedback compensation to design a minor loop transient response that is separate from the closed loop system response. So here we have the problem. For the system of figure 8, we're going to design a minor loop feedback compensation that is shown in figure B, in which the minor loop will yield a damping ratio of 0.8 and the closed loop system will yield a damping ratio of 0.6. So by definition, the minor loop is defined as the loop that contains the plant, which in this case is going to be 1 over s times the parentheses s plus 5 times parentheses s plus 15 and the feedback compensator, which is going to be the KFS. So the value of KF will be adjusted to set the location of the minor loop poles, and then the K will be adjusted to yield the desired closed loop response. Focusing on the minor loop, we are going to get the transfer function of the minor loop, which is going to be G minor loop S is equals to 1 over S bracket S squared plus 20S plus parentheses 75 plus KF. So the poles of the minor loop can be found analytically via the root locus. So the root locus for the minor loop, which is shown on the right, where the KFS over bracket S times S plus 5 times S plus 15 is an open loop transfer function, meaning that the zero at the origin comes from the feedback transfer function of the minor loop. This zero is not a zero of the closed loop transfer function of the minor loop. Hence, the pole at the origin appears to remain stationary and there is no pole zero cancellation at the origin. We see a stationary pole at the origin and two complex poles that change with gain. So as we can notice that the compensator gain here will vary with the natural frequency Wn of the minor poles. Since the real parts of the complex poles are constant here at the negative damping ratio Wn at negative 10, the damping ratio must also be varying to keep damping ratio Wn is equals to 20 a constant. So as we draw the damping ratio line here in 0.8 along the 143.13 angle, it will yield us the complex pole, as you can see on the left, the negative 10. So then the compensator gain Kf is equals to 81.25. We'll place the minor loop poles in a position to meet the specifications. The complex poles we found, which is going to be the negative 10, as well as the pole found at the origin, will act as open loop poles that generate a root locus for variations of the gain K. So those loop poles that we have found here in our minor loop will serve as the open loop poles in our closed loop system. So here we have our root locus for the closed loop system, which is shown on the left. So as we draw the 0.6 damping ratio line along the 126.87 angle, we're going to find the closed loop complex poles found, which can be found here in negative 4.535 with a required gain of 624.3. So K is equals to 624.3, and the third pole is found at negative 10.93.
The results for the approach number 2 example are summarized in this table. You can see that the compensated system, although having the same damping ratio as the uncompensated system, which is 0.6, it is much faster and also has a smaller steady-state error. The results, however, are predicted results and must be simulated to verify the percent overshoot, the settling time, and the peak time. since the third pole is not far enough from the dominant poles. And this is the step response that is shown in the figure, and it closely matches the predicted performance.